Wonderful. And as I said, it's so great to be here. I'm so excited to get to share with you all virtually an update of our most recent exploration with the Curiosity Mars rover. My name is Dr. Abigail Fraeman. I'm the Deputy Project Scientist for the mission, and I'm a research scientist over at Jet Propulsion Laboratory in Pasadena. So let's just do a review about the Curiosity Mars rover and mission. Curiosity landed at Gale Crater, which is about 150-kilometer in diameter impact crater located near the equator of Mars. The key feature of Gale Crater, and the whole reason we landed here, was because in the center of this crater, there's this big mound of material, which from orbit we could see which was layered. This mound is named Mount Sharp. And so the idea for the mission was to land at the base of Mount Sharp and then climb up towards the top, reading the rock record in the layers as we go, and looking for evidence that the layers themselves provided any evidence of past habitable environments. So Curiosity is sort of moving beyond the follow the water that we did with Spirit and Opportunity, and now moving towards looking for environments that were not only wet, but had other ingredients that we know would have made them habitable. So in 2012, Curiosity landed at the base of Mount Sharp, about where the star is in this picture. And since then, we drove towards the mountain and we've been climbing Mount Sharp. So to get a sense of how far we've gone, this is, I think, a really fun image that was taken back on Sol 580. So that was March 24th, 2014. This was our view of the mound from the plains towards the base of the mound. And this is where we are now, Sol 2912, some 6 years later. In total, we've driven about 23 kilometers. If you were to look at this as a straight line distance, it would be about 3.5 miles away. So we've made great progress, and we are definitely on the flanks of Mount Sharp, working our way upwards, looking at the rocks, understanding the past environments. This is a cartoon schematic of where we were and how far we've gone. So Curiosity landed down by this feature called Yellowknife Bay, which we discovered were these lake deposits that were being fed by river rocks coming in. We drove up the plains, we reached the base of Mount Sharp at Pahrump Hills. Again, we started to find more and more evidence of lake deposits as the mechanism that put these rocks down. And at about, say 13 kilometers, we really started, you can see with our elevation, climbing this mountain, getting higher and higher and higher and higher, much more steeply. We, like all of you, experienced quite a change in the way we had to run our missions back in March 2020, when the social distancing needed to help tame this COVID pandemic became really apparent. So our Curiosity operations, a lot of the science team is actually already remote. We have science team members from all over the United States and all over the world. And so a lot of our science operations have been done remotely since landing in 2012. Our core engineering team, though, is still co-located at JPL. These are people like the rover drivers who write the sequences that operate the rover, that command its mobility, people who do things like integrate the plans all together. And those tasks require, as you can probably imagine, a lot of communication between people in a physical space. So it was quite a change for us having to go 100% fully team remote in March, but I have to say I'm super proud of the team. We kind of saw that this might be coming a few months earlier, and so we were kind of in February, we were able to do some practice runs and get our tools set up. And again, we've been running remotely ever since March, driving rovers from our couches and our kitchen tables. Along that time, we have collected many drilled samples. So for the mission as a whole, we have drilled and sampled the rocks of Mars now 29 times. 3 of those drilled samples were actually quite recent. So this graphic that we released isn't even updated to include them. That's why they're off to the side here. And in fact, this last drill, Broken, we actually acquired, we got the data down that it was successful on Tuesday of this week. So drilling this week, we just delivered the rock powder from that sample to the Chemin instrument, which will tell us about the minerals that are present there. So we've been a very productive mission. And again, 6 of these drilled samples were collected since March while we've all been fully remote. The past year of exploration has focused on investigating 2 to 3 major units of Mount Sharp. So from orbit, we could see that Mount Sharp was divided into many different layers, and we could see that the textures and the compositions of these layers were different. And so what this told us was that each kind of set of layers probably preserved evidence of a different kind of environment. So about 2 years ago, we finished exploration of a layer called the hematite unit, which is also known as Vera Rubin Ridge, which I'm not going to talk too much about. And we've since been exploring this unit called the clay-bearing unit, which we've also named Glen Torridon. Beyond the clay-bearing unit, there's another set of layers that are called the Greenheugh pediment, which is this draping unit that is much younger than the clay-bearing unit. And then also sitting on top of the clay-bearing unit is the sulfate-bearing unit. So this is a bunch of layers that we see from orbit have mineralogy that is consistent with sulfates, which are a kind of salt. So our exploration again this past year is really focused on the clay-bearing unit, a little bit of the Greenheugh pediment, and then looking ahead toward the sulfate-bearing unit. So I'm going to talk about what we found in each of these series of explorations. This is just a gorgeous view, I think, of the clay-bearing unit. This is in this area. It's this big trough. It's called the clay-bearing unit because from orbit we saw it had spectral signatures that were indicative of clay-bearing minerals. You can see there's this kind of beautiful wavy pattern that's cut into the rock. We actually think it's probably the way the rock has been carved out by wind. It turns out the rock in this unit is actually quite soft. And it turns out the rocks in this unit, as the name implies, are indeed clay bearing. Interestingly, you can see this Vera Rubin Ridge, the hematite bearing unit, just poking off in the distance. This is a section of much harder rocks that we saw from orbit were associated with the mineral hematite, which is an iron oxide. So different kind of minerals here, definitely different rock hardness, very different from what we see in the clay bearing unit. So the highlights of what we found here, like the layers below, the rocks here were deposited in a lake environment. Curiosity has been climbing about 410 meters of elevation since it landed. 304 meters of those have been on Mount Sharp. And the majority of those 340 meters, including the rocks we found in the clay-bearing unit, were likely deposited in an ancient lake. This is pretty remarkable in and of itself that we found over 340 meters of elevation of rock deposited in a lake. In order to explain that thick a deposit, in thinking about kind of typical rates that these kind of rocks form, that sediment is deposited in a lake, it probably means that the lake was around for millions, if not tens of millions of years. So these data, in addition to providing evidence of a habitable environment, a really clement lake, also provide an important linchpin on the climate of Mars and the past climate in the sense that it tells us that it had to have been able to support liquid water for at least millions, if not tens of millions of years in the past. We also found evidence that the mechanisms that likely distinguish the rocks that are in the clay-bearing unit from the hematite ridge was due to groundwater. We found that the kind of depositional environments that deposited the rocks in this clay-bearing unit and this hematite-bearing ridge off in the distance were actually quite similar. And so what we think happened was groundwater came through at some much later point, hardened the rocks preferentially in this ridge over here, while the rocks in the clay-bearing unit remained pretty soft, and they've eroded away and made this trough. And so that's the reason that these two units look so different, even though they were likely deposited in the same environment at the same time. We've also found by drilling into the rocks and analyzing their mineral composition with the Chemin instrument that they contain the greatest amount of clay minerals seen to date. These rocks are almost 38% clays. Again, these clays form by the interaction of water with the primary kinds of basaltic volcanic rocks that you find on Mars. And excitingly, the type of clay that we found was consistent with what we had predicted from orbit, which are primarily iron-bearing clays called smectites. So this is a nice kind of confirmation that when we think we see clays from our orbital data sets, they are present on the ground. And then finally in this area, we found a whole bunch of interesting kinds of organic molecules, including native sulfur-bearing organics and high molecular weight organic molecules. Now, when I say organic molecules, I'm referring to molecules that at least contain carbon. And, you know, this isn't saying that we found life in this unit, but we've found what could be the building blocks of life. And so it's a really exciting finding, and it's all kind of part of the story that this was once a habitable environment that had all of the ingredients necessary that you would have required to support life. So moving on to the clay, from the clay bearing unit, let's talk about the Greenheugh pediment, which are these very thin kind of gray looking rocks up top. Now, the Greenheugh pediment itself describes kind of the gently sloping surface that comes up, and it's capped by these really thin rocks, which are in fact a sandstone unit. We can see from our orbital mapping that this big sandstone unit actually truncates both the clay bearing unit and the sulfate bearing unit off in the distance. So what this tells us is that the sandstone cap is probably much younger than both the clay bearing and the sulfate bearing unit. And it probably represents a major gap in time. It was probably deposited millions, if not billions of years later after the lake was there and possibly gone. The pediment is also adjacent to this big channel that cuts down Mount Sharp called Geddes Vallis. And within that channel is this big ridge deposit called Geddes Vallis Ridge. And we think perhaps that this ridge formed when water actually carried debris down from higher up Mount Sharp long after the lakes disappeared, although, you know, we're not certain until we can get a much closer look at it. But the idea is studying this much younger capping unit could tell us something about more recent water at Gale Crater. This is a closer view of that sandstone capping unit. I think this is just gorgeous. This is one of my favorite images from the mission. And I'll just go ahead and blow up that center, and you can notice a few things. First, you can notice just the beautiful layers and crossbeds that are evidence in this rock. And as a punchline, I can say we think that this is a coarser grained sandstone, and this probably represents dry environments, windy environments, ancient sand dunes that once moved across the environment long after the lakes were gone that were later cemented by just a little bit of water. But you'll also notice on this lower layer below, just this gorgeous kind of popcorn texture popping out. And what these little spherules actually are probably nodules that formed when you had later stage groundwater, again, interacting with the rock, either coming down Geddes Vallis channel or rising up from the base of Mount Sharp, and they're getting kind of trapped at the interaction where there is this unconformity between the old clay-bearing rocks and the younger sandstone capping unit. So this tells us, again, that groundwater played a really important role in this area, and that liquid water was present long after the lakes dried up. So it persisted for a very long time. We actually climbed on top of this thing, and it was quite an adventure getting up there. There were 31-degree slopes that the rover had to traverse, which is really on the edge of what the vehicle can handle. But, you know, depending on the types of terrain and the geometry of the attack, we knew it was potentially possible. So we decided to go for it to see if we could climb on top and sample this much younger sandstone capping unit. And we made it. And in the process, we set a mission record, again, of traversing these 31-degree slopes. I still think Opportunity holds the record for steepest slopes on Mars altogether. It's something around 32 degrees, but Curiosity is getting quite close with this ascent. This was the view from the top of this sandstone capping unit, just a spectacular view. And again, you can look and see the rocks we were sitting on have these beautiful layers that preserve crossbeds, again, probably an ancient dune field that once drifted over the area. And just to give you a sense of scale, I think this is a really beautiful processing that's done by Thomas Apperet. He went ahead and added 4 Matt Damons and 1 Waldo to the scene to give you a sense of what this would look like when, you know, hopefully one day humans can stand and overlook these viewpoints. So here are the 4 Matt Damons, and if you haven't found it already, there's Waldo, which I think is very cute. So to summarize the highlights that we found at this capping unit, we found that the rocks here are much younger than the lake deposits that make up Lower Mount Sharp. They were likely deposited in a mostly dry, wind-dominated environment. And we still see evidence that groundwater continued to be present here after this unit was in place. So long after the lakes had dried up, groundwater was still playing an important role, which potentially extends the period that this area was habitable. And it turns out this capping unit might be subject to more study as we continue to climb Mount Sharp. So to put everything in context, here's an orbital view looking down. Climbing the mound actually is down in this image. So again, we climbed from this area from Bradbury Landing. We climbed up through what's called the Murray Formation, through the clay-bearing unit, and then we're headed to the sulfate-bearing unit. Here shows sort of our toe dip onto the Greenheugh pediment and the sandstone capping unit. And so we might have another chance to sample the Greenheugh pediment and also this Geddes Vallis Ridge later in the mission. But for now, we're really wrapping up our explorations of this clay-bearing unit, and we definitely have our eyes set on the sulfate-bearing unit, which is the next major unit ahead. This star kind of represents where we are now, and you can see our plans are going to be to hopefully rapidly traverse around this big sand patch that we can't cut through, and then make a sharp turn to the south to continue climbing and reach that sulfate-bearing unit. So what are we up to today right now? This is our current workspace, and we've collected now 3 drills from this area. 2 of the drills are named Mary Anning, who is a British paleontologist who is a remarkable character that I really recommend learning about. And then again, just earlier this week, we collected a 3rd drill sample up here. And this is another view of that outcrop from our HazCam that's located under the belly of the rover. You can see the 2 wheels here now on either side of the image. And if you look closely, you can spot all 3 drill holes in this rock. And you might think, wow, that's an awful lot of drill holes for 1 rock. And this was sort of, we realized, our last chance to sample this clay-bearing unit. And clay minerals in particular are exciting because we know they're particularly good at preserving organic molecules. And so with these drill holes, we were following up on our initial detection of the diverse organic molecules that we'd already seen in the clay-bearing unit. And we actually performed 2 wet chemistry experiments with our SAM instrument. So this is experiments where we mix the rock powder we drilled with a little bit of special called a derivatization agent that makes it easier to detect new and different kinds of organic molecules. So we just did those experiments. They were successful, and analysis of the data are ongoing. Mary Anning, the first drill we acquired shortly after drilling on Sol 2,838. And 13 sols later, when we went to image this drill, you can see this big pile of tailings that we collected that had piled up around the drill hole were completely gone. So it's actually turns out it's quite windy at Gale Crater right now. And in fact, we were able to capture what I think is one of the best movies of a dust devil ever taken on Mars by any rover. This is just spectacular. You can see the dust devil popping up in the faraway hills of Mount Sharp. We think it's about 1/3 to half a mile away. It's probably over 16 feet wide, And we can't actually tell how tall it is because it cuts off the top of the frame. But we estimate it's about 160 feet tall, if not taller. So a really impressive, beautiful, well-defined dust devil in this very windy season at Gale Crater. I'll also comment briefly on some of the atmospheric experiments we've been doing, measuring the composition of the atmosphere, and in particular, looking at the behavior of methane gas in the Martian atmosphere. Methane is an exciting gas to try to track because one of the products that could create methane are biological processes. There's a lot of other processes that could create this gas involving kind of abiotic interaction of water and rock in the subsurface. But what Curiosity has found is that methane is present in the Martian atmosphere at very low concentrations. It seems to have kind of the seasonal cycle. And we've also recently been able to measure the methane at different times of day. Usually we make our methane in the middle of the night, measure it. We were able to measure it in the day, and we're realizing that there is a big difference in abundance that's actually related to the behavior of the atmosphere. So during the daytime, this atmospheric mixing layer is quite large, and the amount of methane is diffuse throughout the atmosphere. During the nighttime, when temperatures get cold, this mixing layer collapses and concentrates the methane near the rover. And so this is one of the reasons that Curiosity has made such a high measurement of the amount of methane in the atmosphere, because we do our measurements at night when the methane is most concentrated towards the ground. I'll just wrap up and give a preview of the road ahead, thinking further ahead. Again, we're wrapping up our exploration in the clay bearing unit. We're gonna drive around this big sand patch, and then we're gonna enter this region that we've called the clay sulfate transition and into the sulfates. And this is exciting because we know that this is a major mineralogical change that we think is potentially reflective of a major environmental change on Mount Sharp. While we've been sitting with our drilling activities, we've actually been taking a lot of images with the remote micro imager on our ChemCam laser ablation instrument. This is the telescope we usually use to look at the teeny tiny little laser shots in the rocks. It's the highest resolution camera on Curiosity, but we've been, instead of pointing it at just our lasered rocks, we've been pointing it off into the distance into the sulfate bearing unit. So this is a beautiful mosaic that again has been assembled by someone in the community. And if you zoom in, you can just see the spectacular layering that's present in the sulfate unit. You know, maybe some hints of cross beds, who knows, but we're really getting excited about the opportunity to get up there and look at these rocks up close in person. So looking ahead, Curiosity is nearing the transition from this clay bearing to the sulfate bearing strata, which again potentially mark a major environmental transition in Mars's history. And this environmental transition was actually a key reason that Gale Crater was selected for the mission's landing site. So as we approach this, we're going to start thinking about what do the data from Curiosity tell us about the nature of this environmental change, and what does it tell us about the persistence of water and habitability on ancient Mars. And to wrap up, I'll just show you, this is just a view we released in the clay unit. Again, looking, this is our path ahead towards the sulfate unit. Should be hopefully smooth sailing, and can't wait to taste those rocks. And you can see also here, here's that pediment capping very finely in the foreground. So with that, I'm happy to take questions in the time I have left.
Okay, has there been any significant degradation of the drill bit?
Yes. So no, actually, we think the drill bit itself is actually doing just fine. We do examine the drill bit after every time we drill. The clay rocks in particular have been extremely soft. It's a rotary percussive drill, so it spins and percusses. And depending on the rate of progress, we can actually up the percussion energy level if needed. And for these clay bearing rocks, we've barely needed to use kind of just level 1 or very rarely 2 out of a possible 5 or 6 in the percussion level. And in fact, the majority of these rocks are rotary only. So we've been drilling some really soft rocks lately. I will say the feed mechanism on the drill is still broken, but we've now collected over half of our drilled samples with this new method of drilling that gets around that.
Okay. How many more years is the mission expected to run?
That's an interesting question. My answer is I don't know. Hopefully many. We are powered, the most limiting factor is probably going to be the power supply. Curiosity is powered by an RTG, a radioisotope thermal generator. So it is time limited because the amount of energy we get from the decay of the plutonium is decreasing year after year. As the plutonium decays, we get less and less energy out of it. You know, we still probably have several good years left in us, but we will start to notice the decreasing energy after a couple years.
Okay. Has the rover found any new surface features similar to the possible microbial mats reported in 2015?
Yeah, so no features ever that are consistent with microbial mats that we've seen. We've seen a lot of features that are consistent with lake deposits, occasional intervals of river deposits and dry wind deposits, but no evidence of microbial mats, no.
Okay. What's the discovery that you personally have found the most surprising?
Oh, the most surprising. I actually think the methane measurements have been quite interesting in understanding the seasonal variability that we see with the methane, and then these occasional spikes that we measure that seem to be almost clouds of methane drifting by, to me have been quite surprising and quite interesting. You know, I also think just the pervasive nature of groundwater at the site to me has been quite interesting, and that it has interacted with the rocks so many times, I think is telling us something really important about the Martian groundwater cycle.
Okay. Do you have contact with researchers who over a longer period of time have personally changed to the Martian day length?
So not only do I have contact, I am one of those people. So I don't know about the researchers who are living in the desert stations. I will say when Curiosity landed, we were all living on the 25-hour Mars day or Mars time. So we did that for 3 months when Curiosity landed. It was quite an interesting experience, you know, going in at 3 a.m. to do our ops and then having our dinners at 8 a.m. and our barbecues. But you know, it's not really sustainable over the course of years and years and years. So all but the people who actually uplink the commands to the rovers now live on Earth time. And to get through that, we'll sequence, you know, 2 or 3 days at a time when needed to cover weekends or times when the Earth and the Mars calendar don't align.
Okay. Can you give a brief about SAM suite in Curiosity?
Sure, yeah. So SAM is one of our instruments. It's called the Sample Analysis at Mars. It is a big instrument in the belly of the rover. And what it does is it basically is a compositional measurement instrument. And so it's one of the 2 instruments that requires the drilled rock powder. And it has a big oven inside of it. And so what we actually do is we deliver some of this rock powder, we bake the rock powder, and then we can measure the composition of the gases coming off of the rocks very finely. And so we can measure things like what are called volatiles. So these are things like water or carbon dioxide that come off the rocks. And then we can also measure more complex, heavier molecules like these organic molecules that I've mentioned. The compositional gas measurement in SAM can also measure the composition of the atmosphere as well, which is how we make our methane measurements.